Yeah, hello everyone. Thanks a lot for the invitation. I have the great honor to give the last talk of the day. It's always the best one. Yes. But at least there's no backwards, so at least you're not so impatient today. Yeah? Anyway, so this is my talk for today. The good thing is it's very light compared to the last talk because the only thing which you have to understand is harmonic oscillator. Yeah? So very easy. Yeah? You will see how it works. Yeah, this is my this is the start of my talk. So this was done in collaboration with Valerie, Tsing, she was a student of mine, Brownian, and John Hao, he's here, and Krishna, he's here. So Krishna is also a postdoc in NCTS. So this is out of my talk. I start with introduction to tell you what this is all about. Then I will briefly talk about the cosmology background. Then I will talk about the matter, and then we'll summarize and conclude. Yeah. So let's just start with introduction. So cosmic relics. Yeah. So I want to explain roughly what the words in my title. With cosmic relics, I mean that are particles which are produced in the universe and which should still be around today. Yeah. The most famous example, which you all know, is the cosmic microwave background, which is well studied, and I will not talk about this here. Yeah. But this is probably the most well-known example. The equivalent to this one is the cosmic Univ background. Yeah. So you know the cosmic microwave background was produced. There was a hot plasma in the universe, and then at some point put as a couple. But the same story should happen with neutrinos. Yeah? I will show you some numbers later, but it usually coupled much earlier than photons. But apart from this, it's basically the same story. The same story. Yeah? And then there is dark matter, which we've only seen gravitationally so far. Actually, we don't really know how it was produced and what was produced by the universe, but to make the CMB work, you would say that you should have produced it before we began, and it should still be around today because we can still see some gravitational impact. Yeah, so all of course in this category. So let me show you some number about the cosmology background. So we know cosmology and we know Zener model and we know neutrinos because of this. So we have some ideas how it should apply. So this should have been produced or decoupled from the 1 second after the Big Bang compared to the CMB. CMB was 300,000 years. Yeah, so that's a huge gap in terms of time. So if we could see this, we could see a much earlier picture of the universe than with CMB. Nowadays, today, if you just assume same cosmology, you would expect roughly 300 neutrinos per cubic centimeter everywhere. Yeah, even in this room. Yeah, so every cubic centimeter should have roughly 300 neutrinos from the Big Bang. The temperature, they should follow our thermal. They should follow our thermal spectrum, and then the temperature is 1.9 Kelvin. Yeah, that means they have an average net energy of 0.5 millielectron volt. Yeah, and the velocity depending on the mass scale can be 10 to the minus 3 up to the speed of light. Yeah, the important thing is, which makes the study difficult, is if you would take the cross section of these neutrinos to 1 neutron, you get a number which is the order of 10 to the minus 3 picobar, or 10 to the minus 63 square centimeter. Yeah, this is small. Yeah, I don't know if you work with cross sections, but for other people that do now is picobar, maybe then they are happy. Yeah, it's slightly below picobar. Yeah? So what about dark matter? You see, there's mostly question marks. We know very little about dark matter. And we don't know when it decoupled from the hot relics, from the hot plasma, and after the Big Bang. We have some idea about the local energy density in our solar system, should be around 0.3, 0.4 GeV. There's some indirect ways to estimate this or determine this. We don't know the mass of dark matter. It can be anywhere between 10 to the minus 22 evolts up to 10 to the 5 solar masses. There's a huge range, and this makes it hard. Yeah, this is actually swing set this much, right? If you would know the mass, it would be done. Yeah, kind of.
Now, what should they abuse after?
Decoupled from the thermal bars after the Big Bang. Good use. Yeah, it's a bit slow, but okay. The local peak velocity, because they cluster in our galaxy, actually they cluster in our galaxy form, we can estimate that the velocity distribution, which roughly peaks at 250 kilometers per second. Yeah? The cross-section ordinary method is also some number which we don't know. We have no idea about this. Yeah, this is also quite a good question. Yeah, so that matter is much more questionable. But people look for dark matter for a long time. The prime dark matter kind was WIMP. And actually, when I was in university, people told me WIMP is basically Neutrino, 100 GeV, SC2 duplet, and you will find it if you build some xenon 100 or something. Yeah, but I didn't find it. And now like xenon 1 ton, and I still didn't find it. The WIMP miracle, the classical miracle, how I learned that I was at university is that there should be somewhat here. But WIMPs are still possible, of course. I'm not saying the WIMPs are impossible, WIMPs are still possible. But right now, people are kind of giving up on the 100 GeV idea and they try to explore other mass ranges. Yeah? And I will be particularly focusing here on the lighter mass range, to go to lighter masses. Interesting. Yeah, this is what I want to do. I want to go towards lighter masses. This is one motivation. The other motivation is this fantastic gravitational wave detectors. I'll show you some pictures which are kind of impressive. So this is LIGO, yeah, here you see the detector arms, and this is not working. Better. So this one here is actually this one is you can clearly see is pendulum. Yeah. So here you see, actually you don't see, I can hardly see it, there's a wire here, and there's another wire here. And this is just a massive, actually it's masses, yeah? These are just some mirrors, yeah? So this is basically a pendulum. That would be important for later. Yeah, why this is so exciting? Because they are so impressively sensitive. Yeah, they discovered gravitational waves. I will not talk about gravitational waves. This is basically all you will see today about gravitational waves. But the interesting thing is that they're very, very sensitive, and this I want to explore. Yeah? So the question I want to ask is, can we use these experiments to look for dark matter? Or neutrinos, cosmic backgrounds. So let's start with cosmic backgrounds. So this goes back to 2017. So the idea is very simple. Yeah? So we have this very, very sensitive pendulum. In terms like we can measure their position very precisely. And neutrinos, this cosmic neutrino relics, they are everywhere around us. And because the Earth is moving in this neutrino bars, there should be something like the wind of neutrinos coming in. That means I should give like a very gentle push to this pendular masses. And then we want to measure the position and see if we can find this displacement. Yeah? And because the Earth is rotating daily and annually around the sun, there should be some modulation of the direction of the wind, and that means that the pendulum should slowly move and follow the wind. Yeah? This is the idea. Yeah? So you have like a cosmic background wind which pushes your pendulum around over the time of the year. Yeah? So we can make some very nice estimates, accelerations which we can test. This is G factor on Earth. This is 9.8 meters per second squared. L is the length of the pendulum, and D is position of solution achieved. So we took the LIGO numbers and interpreted them generously, and we found this bound that LIGO can test maybe 10 to the minus 16 meters per second squared. This is a tiny acceleration. Yeah? This is a very tiny acceleration. Telescope, which is like the future of this business, that they might reach something like 10 to the minus 18 meters per second squared. Yeah? Just to give you some numbers. Then we can do some calculations. I will skip this part because I want to limited time. The good thing is because we know this so well, we can calculate this and make some estimates. The bad thing is that this number is slightly too low to be tested. But yeah, that's just how life is. Yeah, sometimes you win and sometimes you lose. But yeah, I mean, as a good scientist, if something doesn't work, you think about other things. So we had a look in other systems. Solar neutrinos, actually, it turns out they are not so much stronger than the CME neutrinos. This is because of some coherence effects. But then for dark matter, for the ordinary cold weak dark matter, with more than 1 GeV, you're also very much limited because the cross section is very tightly constrained. But if you go to lighter dark matter masses, because the constraint in the cross-section becomes so much weaker, like really weak, like many orders weaker, there might be some room that you can do something. Yeah? And this is something that we wanted to explore further, and this takes me then to the dark matter part. Yeah? The dark matter part, I want to split into two parts. First, I will talk about this in language which particle people can understand. Then we talk about it in a way how gravitational can see. Yeah? And I hope most people can learn something from each other, because I do. Yeah? So now I somewhat changed the picture slightly. Before I was basically talking about some integrated effect, average effect of the neutrino scattering. Now I really want to go and look and take the mass, the test mass, the pendulum mass, and I observe its position, and I really want to look like when the viewer scatterings. Yeah, like some dark matter comes and hits it, and then gives it a small push. And another dark matter particle comes, hits it, and gives it also a push. And this one is basically Brownian motion, because the dark matter particles come from all directions. There's preferred direction because we're moving within the dark matter bars, but this is basically like, it's like Brownian motion basically. Yeah? So this is what I want to observe, and then what I do is I take all the scatterings, I look in which direction it goes, like forward or backward, like one information, and then I find some symmetry, and this is really my observability. Yeah? So I show you some more pictures. So this is a slide which I took from my student. She's now in Heidelberg. This is basically what we propose. We take some setup. This is actually not important. Really, we don't need a laser. I don't care about lasers. Yeah, so this is just some device, measure the position. Yeah, so we have some movable object which should rest, let's say, and then it should get some push. Yeah, so this is the idea. We measure this position in the x direction, and then we know the system well. So we say if there's no external force, that should be here, but if it's here, we say, oh, there was a push between these two data points, and it's pushed in this direction. Yeah, and then we just say, we just count off all of them. Yeah, how often do we get a push in positive x direction? How often do we get a push in negative x direction? Yeah, just counting how many events. Yeah? And if you do this, you can simulate this. For that matter, you should get something like this. Yeah, because in the preferred direction, most pushes are very gentle, so very weak, very small Nickel momenta, but you see there's some clear asymmetry. Yeah? There's much more going to plus and going to minus, and then you can calculate this asymmetry parameter, which is like forward backward asymmetry or CP asymmetry or whatever. Yeah? If you're a particle physicist, you know it's very good. Yeah, then you can look at the modulation of this A. So this will be in Tsing on June, I think it was in June 1st. Yeah, this would be in east-west direction, and this would be in north-south direction. Yeah? The modulation of this A parameter would measure this. Okay, then there's the problem for the, this is all theory. Yeah? Of course, I can always write this down, but then the question is, can you really see this or not? So this is a bit tricky to answer because we don't have an experiment, and many background questions you can only answer if you know the experiment. Like, what about seismic noise? Well, this depends on location. Yeah, nearby traffic, that depends on location. Relativity, that depends on location and the materials used. Yeah, so there are many backgrounds which are hard to discuss if you don't really do the experiment. But there are two examples which you should for sure have, and we try to explain how you can try to test them. Yeah, one example is neutrinos, which means you can shield. So wherever you are on Earth, you will have neutrinos. Another one is hits from residual gas. So let's start with the neutrino cross sections, neutrino part. This is actually very easy because we are aiming for light targets. So we're talking about milligram targets. And if you have milligram targets, neutrinos don't care, they just go through. Yeah, and you know this because neutrino experiments are large, very large. Yeah, so you just scale this, and then you have like a tiny target mass. Yeah, you basically never get neutrino back. So the event rate for neutrinos is just super tiny, as long as your target mirror mass is below a kilogram scale. Yeah? So this one is easy to discard, yeah, because we have no events. What about residual gas? This is more tricky. Yeah, so if you do this, again, for time reason, I don't show details. We can discuss later. I can look into my paper. Naively speaking, you get even in an ultra high vacuum. Yeah, we're talking LIGO has some ultra high vacuum, and CERN has some ultra high vacuum. It's like 10 to the minus no, I forgot the units, super high vacuum, very, very good vacuum. Yeah. But even then you still, sorry, I think I pushed some button. Yeah, I can wait. Good. Maybe now I moved myself. Anyway, so usually you would expect something like 10 to the 9 events per second. Yeah, even if you have a very high vacuum, you cool your chamber down to 20 Kelvin, like in KAGRA. This is what you get. But then this is not a relevant noise in KAGRA actually, which you might find confusing because if you say you have so many hits on your mirrors, how do they not care about this? So the reason is that KAGRA and LIGO, they can only resolve a finite momentum. And this momentum is kind of high compared to the average hit. Yeah? So that means actually after you apply this cut, all of these events are gone. Let me just maybe show you a figure to make this a bit more clearer. Let's just assume this would be the distribution of the little gas hits. Yeah? And basically what's saying is that LIGO and KAGRA, they have a cut here. So basically there are no events left. Yeah? And if you're lucky, our dark matter distribution is broader than the little gas distribution, and then we're in the game. Yeah? Then we can do this. And of course, this depends on the properties of dark matter, and of course, it all depends somewhat on the experiment, how you organize it. Yeah? But this is what we did and what we assumed. So here we just let me just explain this. So this is our final result. If you want, this would be the constraint of the cross section for dark matter scattering with nucleons, and this is dark matter mass. So these are some real experiments. This is Edelweiss, Crest, 2017, 2019, this is CDEX. So you see here, I start here at 1 GeV. Yeah, so here I focus on light dark matter masses. That's why there are not so many constraints here. So for a perfect experiment with 1 milligram of carbon, if you take 10 minutes of data, I'm not talking about years. And you would have no such thing as some minimal momentum resolution, no background whatsoever. We could basically exclude this black line. Yeah? If we include that we have a finite momentum resolution, yeah, we have like a minimum momentum which you can resolve. We assume this number, which you can kind of also take from LIGO if you're generous. Then you get here this vertical line, so we cannot find that better which larger than this one because basically then you don't get any events which have larger momentum. Then you start to see something, you can start to exclude something, and then you get this kind of constraint in theory. Yeah, this is an expectation, yeah, which you could up. Yeah, so as many experiments are like this is too optimistic, but this is a privilege of the theories. Yeah. So let me move on to the other side. Yeah. So also when you were writing this, especially gravitational, people get very confused. And they said, is it all impossible? It's all impossible. So I thought, let me try to understand if this is actually really not possible or it's actually possible. And the same thing is actually possible. So how does it work? So now I'm talking about really again, going back to, it's all a harmonic oscillator. Yeah, it's all pendulum. I'm just talking about pendulum. Yeah, pendulum, this is a pendulum. Yeah, here. Yeah, you see, harmonic oscillator. And then I have, this is the spring constant, and here introduce some damping factor, which for some specific reasons I write it as 1 plus I pi. But this is also how KAGRA does it, and there's some reasons for this. Yeah? And then I just have an external force, and this external force would be dark matter forces. Yeah? But then there's also noise components, and the ones I care most about, which was the dominant components for KAGRA. In the window is like suspension turbine noise and quantum noise. So just mention quickly, our work was on the noise. Yeah? So I just cite here the results. So there is the terminal noise from saturation dissipation theorem. How does it work? So the one-sided power of the density is given by this formula. So you see it's proportional to the temperature, thermal noise, and this one here is the real part of the admittance of the system. That is basically the mechanical response, the linear response of your system. Yeah, if you look at this more closely, you see here there's the omega c is the resonance frequency of the system, phi is the damping of the system. Yeah, it's basically like the Lorentzian, and then it's an extra factor of 1. Then there's the Sonic quantum limit. Let me just explain this. So this is thermal fluctuations. Yeah, this is just because it's a thermal system. Sonic quantum limit is because you want to measure the position of this object, and these experiments are so sensitive that they are working at the quantum limit. That means you know that you cannot at the same time equally precisely measure position and momentum. So you have to make a trade-off, right? Because you also want to measure the position of something not only at one time, but also at several time steps. So you always get some uncertainty, in terms of momentum and position. So you have to make a trade-off, and if you minimize this, and you get this this formula here, which is also just a theoretical thing. So let me just work with this one here for the moment, and then we can get the noise and amplitude. And this is the quantities gravitational we talk about. So this is the noise, and let me talk briefly about the dark matter part. So for dark matter part, it's here to talk about some material differential equation for your pendulum, because then you also get real displacements, and then you have some damping here, some eigenfrequency here, and this is the crucial part. This is the dark matter force. The dark matter force here we just give as some delta force, so we just have hit, and we cannot see any details or the time resolutions to that. We just see basically before it and after it. And difference before it and after it is just the convention. So the only thing we do is at time t to 0, we inject some momentum into the system, which comes from dark matter. This is a QR, so it's momentum. And L, by the way, is the length of the meter arch. This I can give my undergrad students to solve, and if they're lucky, they can do this. That's the solution. And then we need the Fourier transform. We take the modular square of the Fourier transform. This is also do. But now we have the problem that the equilibrium equation which matches to the complex one, to compare it to KAGRA, for instance. That gave us some headache for some time, but then we decided to measure it this way. So what we say is the oscillation frequency and the damping should be identical in both cases. That is a reasonable assumption. And then you find that the real oscillation frequency is the complex oscillation frequency, the resonance frequency, with this correction here. And the same for the damping. You see that the complex, now this is the real damping, compared to the complex damping, is equal up to a factor of 2 plus some correction. And I should also say that for KAGRA, this phi is super tiny, 10 to minus 6. So it's really a small correction. So if you rewrite this dark matter signal, then in terms of complex quantities, this is what we find. So the formula becomes much simpler and much nicer. And important is here that the suspension terminal noise and dark matter signal are at the same frequency, resonance frequency. They have the peak at the same frequency. And this is an amplitude. Let me just show you a figure. So here I plot the straight amplitude. This is the quantity the LIGO and KAGRA people always plot which is the frequency domain. And then here on the horizontal axis we have the frequency. So this is a dark matter signal. For a Taiwan model where we just have one resonance frequency here, and here I assume KAGRA-like parameters. So the parameters we choose here are taken from KAGRA models and assuming something like 1 GB dark matter particle. Then here we have the thermal suspension noise, which is larger, and there's also the Sonic quantum limit, which you all see is here actually the dimension is larger than the quantum. Okay, let me just speed up a bit. So let me talk about this noise ratio. This is a formula which is also used in gravitational people, at least as far as I know. I'm not the gravitational person. If I calculate the signal to noise ratio, what I find is if I take it over the full width of maximum peak, if I get quantum noise, because you saw this near the peaks, this is negligible, I find that this is equal to this ratio, and this is equal to the ratio of the recoil energy divided by the thermal energy. And it tells me if I want to make this larger, if I want to see a signal, what I should do is I should take first of all much colder mirrors, and I should also take much lighter masses, target masses. And then I can make this, as a theorist, I can make this as large as I want. But anyway, we'll come back to this. So this is an important lesson which we learn and quantify. This is important. We can quantify it. Yeah. This is something I was need to understand. Yeah. From just think about it. You say, better take light than contact. But this is really a formula. Yeah? This is not just something you guess. So this is KAGRA very briefly. We look at KAGRA because Taiwan is part of KAGRA. I also become a KAGRA member. It's good is because it's cryogenic, temperature is 14 Kelvin. It's a triple pendulum. Blah blah blah. If you do this, your equation motions become matrix value equations. Because you have coupled harmonic oscillators. The force also becomes vector. Then you get a very complicated spectrum, lots of resonance frequencies from suspension system, lots of violent modes. That's why you get so many things here. The quantum noise also gets more complicated. This becomes this blue line here for various reasons. Anyway, we can use this formalism very quickly, and then we get some results. So here, this is the terminal. This is the noise from KAGRA, the black line here, total noise I showed you before. And then here, this is what you would get if you would have dark matter here with 1 GeV in the mirrors, itself, in the test mass. This is what you would get. If you get a hit in vertical direction, this is what you get if you get a hit in horizontal direction. Keep in mind that you can basically test two directions, and the question is in which direction the incremental points. In general, there will be of course combinations too. It's just here we just take two water combinations. You can also understand this picture here. There's some cancellation going on because you have multiple resonances. There's some cancellation going on. But I have only like 3 minutes left. So this is if you hit the plate springs and not the mirrors, and this is what you get if you hit the limit mass and not the test mass. So you see, depending on where you hit, you get different spectrum. What I want to highlight is that's important is that when I say, I want to light masses and light and cold masses, this is not science fiction. They're actually people who use this. This is called optically levitated masses. So they use lasers to levitate the masses, and they talk about 1 nanogram mass. Temperature is 200 microkelvin, and here they actually do this to look for dark matter. This came out shortly after we published our paper. The problem, but if you look at this, the experimental threshold is 0.15 GeV, which is still rather large. This is because they are not working at the quantum at all. We're talking about small scale experiments. We talked to them and they said, if some persons in the lab, we can see it in our data. This says that their experimental setup skills still can be improved quite a lot. Just by not being there. By others, but they will improve, and I don't know how good they will become, but this is something I'm very optimistic about. So let me come to my summary conclusions. So gravitational astronomy has just begun, and this is very exciting. But I'm not working on this, so I'm too old. So what I like about this is that impressive technologies. This really impressive. Basically, they operate 20 kilogram masses at the quantum limit. This is really remarkable. And I'm wondering more, can we use what they are doing for more particle physics or cosmological purposes, and astronomy purposes. So what I try to explain is that for cosmology background, it's a neat idea, but it doesn't work. Probably. Let me say probably, because who knows? Maybe in 50 years, somebody can do this. But for dark matter, maybe. So KAGRA itself for 1 GeV dark matter doesn't work. There are other proposals for very light dark matter, very heavy dark matter, where KAGRA might need to say something. I don't have time to talk about this now, but there's some other ideas which might work. But for dark matter, this kind of technology is very interesting. We might really explore some regions which you cannot really see in conventional dark matter searches. There's also this optically levitated masses, and there's some other proposals, which go in this direction. And also people talk about just looking for dark matter using just gravitation interactions, which is quite interesting. So what I would say is need more research. This kind of technology is young still in a sense. And we need more research to explore this, what we can really do or not do in the future. And I think this is good because definitely in 10 or 20 years, we'll know much better what dark matter is not. Yeah? So this is also something. Yeah? Yeah, that's it from myself.
The two questions. This question is about, I learned from you with so solar neutrino is the energy slightly higher than CUV. And then if this CUV doesn't work, why can you work on the solar neutrino? And then for the same idea, the same question is recently a dark matter come from atmosphere. People thinking about also about atmosphere or PP collisions, they might produce the dark matters. And then those of the things maybe give a different frequencies or something. Is in your detector range or something.
Let me answer your first question first. So, for solar neutrinos, it doesn't work because the point is actually the energy is very different. So, CRB neutrinos have MEV and solar neutrinos have MEV. So, you see the difference. It's a small m and a capital M. So, it's a factor of 10 to 9 difference in energy. And this, in terms of cross section, is a huge difference. But the point is that this CRB neutrinos, they get a coherence factor boost, which the solar neutrinos don't get. And this means that for this study, actually the acceleration was very similar. And you also know, I mean, talking now about kilogram or even lighter targets, and then solar neutrinos have no cross section. Yeah, you need kilos, 100 kilograms, a ton, 20 tons, then you can use solar neutrinos. Yeah? So this is a stupid way for neutrinos. I learned after I calculated. So the second question, so it's a good question in some sense. Let me just say the spectra, this form of the spectrum is given by the mechanical setup of the experiment, not by dark matter properties. The only thing for dark matter properties which you can discuss is basically the direction where the recommended comes from, and then you get a combination of these two, a linear combination of these two. Yeah. So of course what I didn't want to do is because I wanted to focus on dark matter, but of course you can discuss like heavy dark matter, or you can discuss about boosted dark matter stories. And then because the momentum which you expect becomes larger, all of this shifts up. It's just a vertical shift. Yeah, this is proportional to QR, right? QR, Q squared, QR. So if you have a larger momentum, it just goes up. It's really proportional to QR. But the point is why the audience must do this is all the stories when you expect a larger QR, what you expect is also a smaller number density for this dark matter. Or event rate, if you want, the event rate goes down. Yeah? And then at some point, if you say I have only one event every 10 years, it's very hard for KAGRA to say that was dark matter. Yeah? Because here, what you should really do to identify that this is dark matter, you should look for some kind of correlation pattern. That means you should look for many of these kind of hits which you can't quite identify, and then do the scale of time to reconstruct the direction, and then say there was a modulation which fits the dark matter. Yeah, you can definitely do this, but I didn't want to do this here. But you can play this game.
Other question?
This is a very interesting idea. So I have a question. Once this detector is able to detect the dark matter signal, and in principle, that it will also receive a bunch of noise from gravitational waves, right? And is it easy to handle this noise?
Good question. So the point is here, I took KAGRA as an example, but KAGRA was made to look for gravitational waves. So they have their sweet spot for their detection is somewhere around 100 Hertz, 50 to 100 Hertz. But for me, I don't care where I put my frequency because my frequency is only by the mechanical resonance frequency of my system. But dark matter excites all frequencies. That means I can push it to any frequency I want, and I should push it to some frequency where I don't expect too much background compensation. And then I will try to engineer this to be optimized for dark matter, not for gravitational waves. And also even KAGRA, I mean, it's not that there's so many gravitational wave derivatives. But yeah, of course, you would try to want to make it steeper, but then I can shift my frequency, and I have no preference for frequency.
That's it. Thank you.
Anything further? If not, let's thank Martin again for a wonderful talk. So that concludes our today's session. So yeah, so 2 more days to go. So let's just see early.
Huh?